Stanford University.
You asked me about reheating, heating. This is the subject of cosmology, of course, early cosmology. So the original, and especially inflation, reheating is what takes place at the end of inflation. Inflation is the exponential expansion of the universe, and it's driven by, depending on your taste, what is sometimes called dark energy, what is sometimes called the cosmological constant, or vacuum energy, whatever you like. But really, what it's got to do with is the energy stored in a scalar field of some kind, a potential energy that's a function of a field. So imagine a field, phi. This is not space-time. This is just a plot of potential energy versus the field phi. And phi is called the inflaton field. Phi has a potential energy. Of course, it has a kinetic energy. The kinetic energy of a field is just the energy that's stored in the time derivatives of the field. It also has a form of energy which is usually counted as kinetic energy in our lingo. It's not got to do with time derivatives. It has to do with space derivatives of the field phi. So if phi has a gradient from place to place, there's an energy stored in that. And while it's not, strictly speaking, kinetic energy, because kinetic energy has to do with time derivatives, because of the similarity of space and time in relativistic physics, any energy that has to do with the variation of a field from point to point in space-time is often called kinetic energy. So that's a form of energy. But then there may also be a potential energy to the field. A potential energy is just an energy which doesn't depend on gradients of the field. It doesn't depend on time derivatives. It just depends on the field itself. It's an energy density. And you're free to make up your own favorite model. This field phi has never been discovered in the laboratory. Its quanta, it certainly has quanta if it exists, have never been seen as particles. And that's bad because it doesn't tell you what to do. On the other hand, it's also good. It says you can do anything you want to do. All right, so let's make up a potential. I'll first draw you the kind of potential that physicists or that were thinking about when this idea of inflation started. They had in mind a potential energy which the historical reasons why this particular form was imagined had to do basically with the Higgs particle. But we don't have to go back to the history of it. I'll just show you what was originally discussed and what's wrong with it. So a potential energy which looks like this. This potential energy over here, when the field was right at the center, when the field was equal to 0, was imagined to be very large. Potential energy way beyond, it's an energy density, but it's way, way beyond anything experienced in the laboratory. A huge amount of potential energy at the center. Even more as you move away from the center. But then as you go over the top of a hill, you can imagine if this were a particle moving in a potential, if you managed to get over the hill, you would just zip down to the bottom of the hill. Okay, so the idea was that originally, for reasons unknown, the universe started with the field equal to 0. That's a stable position, a stable value of the field. It cost energy to displace this. So if the field started out as 0, it would just stay that way. It would be like a ball rolling at the center, not rolling, just sitting at the bottom of a hill. It's not going to do anything. But lots of potential energy. Potential energy counts as vacuum energy. It counts as dark energy. It causes the universe to exponentially inflate, and the inflation rate is determined by the amount of energy there. That's fine. The universe exponentially inflates. That's good because it flattens the universe, it irons it out and makes it smooth, and it is consistent with what we know about the origin of the universe, that the universe was very smooth and flat to begin with. And so this very large amount of inflation which may have taken place here is a good thing. It brings the universe into conformity with flatness and homogeneity, isotropy, uniformness, just by the inflation and the stretching. But then it just leaves you here. So what happens next? Well, the idea was what happens next is if you wait long enough, what happens if you have a particle or an object stuck in the bottom of a hill like that in quantum mechanics? Tunneling. Sooner or later, just by quantum fluctuation, something happens that would never happen in classical physics. In classical physics, there's no way to get over the top of this hill unless you're provided with enough kinetic energy to get over the top of the hill. But in quantum mechanics, everything that can happen does happen. And the point, of course, is that the wave function of a particle is not really concentrated at the very center. It has an exponential tail which leaks out into the region on the outside. And that means with a very, very small probability, if you wait long enough, the particle, or whatever it happens to be, will suddenly find itself on the outside and then roll down the hill. Okay, this is classic, not classical, but classic quantum tunneling.
Does that mean it does it everywhere in the universe?
Well, okay. That's exactly the point. The original idea was the hope that it did it everywhere simultaneously. This great big inflating universe just dumped its energy, dumped its vacuum energy into kinetic energy of rolling down the hill, and that kinetic energy, like any good kinetic energy, will eventually get converted to heat by some way or another, whatever the mechanism is, and that heat was the heat that originally heated up the universe. But then, as was just asked, and it should have been asked from day one, is it really reasonable to suppose that this universe, which is inflated to exponentially large sizes, will everywhere simultaneously undergo this process of tunneling? And the answer was no. It didn't make any sense at all. The way quantum tunneling of this type takes place, the universe expands to something very large. This blackboard now is the universe. It's e to the e to the e times bigger than anything you want to think about. And the value of the field everywhere is at the minimum here, at the minimum of the potential. What can happen? The probability of it simultaneously everywhere is going zip over the top of this hill and coming down here is extremely negligible. What is much, much more likely is that a little bubble will open up. A little bubble. Inside this bubble, outside the bubble, the field takes on the value at the center here, phi equals 0, let's say. Inside, a little hole opened up where the field is equal to, let's put it over here, phi a, let's call it, phi a. Now, these things are constantly happening in the quantum mechanical vacuum. Fluctuations are constantly taking place. But for the most part, those little bubbles that form, they're little bubbles, and they're very, very similar to what happens if you have a pot of boiling water. Little bubble forms. And in fact, those bubbles will form even in the pot of water if the pot of water is below the boiling temperature. You'll get little bubbles nucleating. But the little bubbles, if they're too small, will be squeezed out and just driven back into the phi equals 0 phase. So unless the bubble achieves a sufficiently big size, and the same is true of bubbles of steam, and in particular, a good example from ordinary physics is what happens if you cool a liquid, for example, below its freezing temperature. If you cool a liquid below its freezing temperature, but you cool it very, very carefully, it can stay liquid. But if you put in a tiny chip of ice, take the case of water, you put in a tiny chip of ice, the chip of ice will form a seed, and that seed will start nucleating around it more and more crystal, and that crystal will grow, and will grow very, very rapidly and fill up the whole sample. So a bubble, that's if the bubble or the little seed is big enough to begin with. If the little seed is too small, then what happens is a kind of competition, and what wins is that the water around it will cause the little crystal to melt back into the water. So a tiny little crystal of ice, if it's too small, will not start the process off. But if it's bigger than a few dozen molecules on a side, it will begin to grow and simply eat up the whole thing. Now, of course, because of either thermal fluctuations or quantum mechanical fluctuations, you don't really need to put a chip of ice in there to get this thing going. All you need is to wait until accidentally, just purely accidentally, a significant number of molecules happens to orient themselves in a form that looks like a crystal, that looks like a little chip of ice. From time to time, that will happen just spontaneously, just by the statistics of a few molecules. It doesn't take many of them to start the process going. Just by accident, if a large enough number of them happens to form a little piece of crystal, by pure fluctuation, then this process will happen by itself. So if you wait long enough, yes, a little lump, a little bubble of ice will form in the metastable water. Of course, if your sample is big enough, then simultaneously a bubble may form over here, a bubble may form over here. And what will happen? They'll come crashing together. They'll start expanding, and after a while they will have expanded and they'll come crashing together, and the result will be the entire sample, the entire collection of fluid will undergo this transition from liquid to solid, for example, or it could be from gas to liquid. That's the nature of a metastable bubble nucleating fluid. Well, that's about what would happen here. If you wait long enough, a small bubble will form. If the bubble is too small, it'll simply get squeezed back into the original vacuum. I call this the vacuum over here. But if it's large enough, it'll start to grow. It'll start to grow and grow and grow and simply gobble up more and more space. Now, what happens? You say, okay, good, that's fine. Another bubble forms over there, another bubble forms up there, and soon they come crashing together, and the result is the entire universe has made a transition and goes, and just like the ocean, if it were metastable and you ticked off a little bit of ice, the same thing would happen. But that's not what happens in cosmology, and the reason is that the regions in between are expanding rapidly. The regions in between are here. They have this value of the field, where the vacuum energy is large, and large vacuum energy means rapid inflation. So the region between these bubbles is growing, and it's growing even faster than the bubbles themselves are growing. Actually, there are two possibilities. It depends on details, whether the bubbles grow faster, nucleate faster and grow faster and outrun the expansion, or do they separate from each other so rapidly because of the inflation that they never hit each other and they never complete the transition? Well, with all of the numbers being put in there for a sensible theory of inflation, what wins in this type of model is the inflation is much, much more rapid than the nucleation rate. And so what happens is these bubbles never catch up with each other. They never catch up with each other because they're being driven apart by the repulsive effects of this vacuum energy. And so the phase transition, the words are the phase transition or the transition from here to here, is never completed over the whole universe. It's just a collection of bubbles. And a collection of growing bubbles is not the kind of homogeneous universe that inflation was intended to create. This is a first-order phase transition. A first-order phase transition is what happens when you have a barrier to, when you have two phases, a phase here and a phase here, with an obstruction in between, and that obstruction is called a domain wall. An obstruction from going from one to the other is called a domain wall. The boundary of this region over here is called a domain wall. And it's the place where the field goes from here to here. To get from here to here, from inside to outside, it has to go through a region with a much larger potential energy, and that's costly in energy. So the result is that the phase transition doesn't happen. The entire universe doesn't reheat in this kind of first-order system. And it wasn't the right idea for reheating. Was just this idea that the entire universe goes plop over into the other phase and creates a lot of heat. All right? That doesn't happen in this kind of theory. All you really had to do was remove this bump here and draw it more like this. Whoops. And for whatever reason, start the universe up here and just have it gradually roll down and all simultaneously. That is what does work. So, but that's not the kind of first-order phase transition that was originally envisioned. All right, I answered that because somebody brought it. I didn't bring it up. Who brought it up? You brought it up. Okay. Answer the question? Good. Okay. Yeah. All right. So let's come to this question that I've been avoiding for a couple of weeks. It was a very good question. I sort of gave you the answer, but let me quantify it a little bit more. It had to do with adiabatically varying parameters, such as volume, but it doesn't have to be volume. Any parameter that you can vary. It is true that the entropy defined in terms of the probability distribution stays constant during an adiabatic change of parameters of a system. But in general, the system will not stay in thermal equilibrium. And I mentioned the reason. The reason is that the probability distribution, which was e to the minus beta, let's call it E sub I, where I is the ith energy level of the system. That's the probability distribution. We have to divide it by the partition function, but that we can do that. That probability distribution is maintained with time as we change the parameters. But as we change the parameters, the energy levels change. And what started out as e to the minus beta E sub I will not, let's say each E sub I goes and becomes, let's call it E prime sub I. This probability distribution, which is what we started with, will not become e to the minus beta, even with a different beta in general, even let's call it beta prime, E sub I prime. Somebody sent me an email with an example, almost any example you think of, that will lead you to a probability distribution that cannot be equivalent to thermal equilibrium for any value of the temperature. It's just not the way these things work. Somebody sent an example with 2 spins. It's very, very general. Okay. Now, is a very special case. There's a very special case where you can say the system stays in thermal equilibrium. It's very, very non-generic. But let's suppose that E prime I is a linear function of EI. In other words, let's suppose that the final energy after the adiabatic change of parameters, E sub I prime is a function of E sub I, or E sub I, if you know E sub I, then you know E sub I prime, assuming you know how the energy levels change. If these are related by a linear relation means E prime I is equal to some A plus B EI, where A and B are fixed numbers, then this probability distribution, well, let's do it the other way. If something's a linear function of another thing, then the other thing is a linear function of the original thing. Let's do it that way. Then the original probability distribution is also equal to e to the minus beta. Then let's write E sub I, A plus B E sub I prime. All right. E to the minus beta A, that's just a number. Okay, that doesn't even depend on which energy level we're talking about. That will eventually get absorbed into the partition function. The important part of this is the part which is just E to the minus beta B E sub I prime. Okay. If this were the case in general, then all that would happen is we would say the original thermal equilibrium becomes a new thermal equilibrium with beta prime equaling beta times B. So that's the one special case where the energies are linear functions of each other, where you don't have to worry about it. Thermal equilibrium stays thermal equilibrium. Okay? But as I said, this is not very generic. So what's going on? Okay, let me point out one more thing before we go on. The answer has to do with the system being large. It's quite true that if you take a small system with a few degrees of freedom and it's in thermal equilibrium, you then isolate it and insulate it, change the parameters, it will not stay in thermal equilibrium. It just simply will not. Okay? But if you have a big enough system, a large system, then you find to a very, very high degree of approximation it stays in thermal equilibrium. So why is that? Okay. The energy of a large system, now I mean a system with large volume, the energy of a large system can of course always be written in terms of the energy density. Let's call the energy density epsilon times the volume. Now that's not particularly helpful in this context because there's no more likelihood that the energy is a linear function. Let's go back. The energy of the system both before the adiabatic change and after the adiabatic change is proportional to the volume. So that means both E and E prime can be written in terms of energy densities. It's the energy density you can think of as changing when you change the parameters of the system. Let the energy density be the thing we'll follow. Now, there's no more reason to think that epsilon, the energy density, are linear functions of each other than there is to think that E is a linear function of E prime. So this hasn't helped. Knowing that the energy is proportional to the volume doesn't help you understand in what sense the energy is the two energies are linear functions of each other. But it does tell you something. So let's see what it says. It will be useful. Okay. When a system is very big, the energy levels are very dense. Not dense in space, they're just many, many energy levels per unit energy. Many, many energy levels per unit density, per unit energy. You can write the partition function as an integral over energies just because the energy levels are so fine-grained like this. Fine-grained not in space, just in terms of energy. Energy vertically, levels plotted, many of them, and they're extremely dense. And what's more, in other words, the number of energy levels per unit energy gets very dense when a system gets large. All right? Moreover, the density of these energy levels grows very rapidly with energy. If you look at the ground state of a system, there aren't too many energy levels nearby. If you increase the energy, there are so many ways of creating a large amount of energy. There's only one way of having the ground state. There's only one way of exciting it to the first excited state. But if you excite it up here to some relatively large amount of energy, then there will be many levels in there, and that's a typical situation. So the number of levels, the number of energy states per unit energy is a very rapidly rising function of the energy. That's the key. Let's call it the number of energy, the number of levels per unit energy. That's a very rapidly rising function of energy for almost all systems. In fact, for all large systems, meaning systems containing lots of molecules or lots of degrees of freedom. Very rapidly rising. Now, what do we have to do to compute the partition function? To compute the partition function, we want to sum e to the minus beta e sub I. We want to sum it over all states. In this limit, when the density of levels is very large, we can replace this by an integral. E to the minus beta e dE, but that's not the end of the story. We have to include in here the number of energy levels per unit energy. What we're doing is we're counting the energy levels, putting in each one with an e to the minus beta ei, but we have to ask how many energy levels are there per dE. And let's give that a name. I'm not sure what to call it. Well, we can call it dN by dE. The number of levels per unit energy. And it's only if we put this factor in that we will be calculating the same thing as the sum here, or even approximating it. So it's the integral of e to the minus beta e, dN by dE, where dN by dE is a very rapidly rising function of e. On the other hand, e to the minus beta e is a rapidly falling function of the energy. Okay, so we have the product of two things, one which is rapidly rising, the other which is rapidly falling. And the result is that the product of these two things is typically concentrated in a fairly narrow, very narrow in fact, range of energies. Let's call it delta E. All right. All that's really important to this argument over here was that within the range of energies, at a given temperature, of course, this range of energies is narrow, but it of course depends on what the temperature is. This function will move, the peak in this function will move around as we change the temperature. As we change the temperature, the falling function changes. The falling function changes as we raise the temperature, for example, and that will move the central peak around. It'll also move the width of the central peak around. But for any given temperature, there's a central peak and a little bit of fluctuation around it. All that's really important is that over the range of energies which are important under this distribution here, that within that range, that this function be linear. Things outside here are terribly unimportant. Only things inside this peak are important. And so as I say, the important thing is that the relationship between energies before you vary the parameters and after you vary the parameters is linear over the range of energies which are important under the integral sign here. All right, so let's ask, is that likely to be the case? Let's go back to the energy density. The energy density, again, will have no reason to be a linear function. The only thing we can expect of it is that it's a smooth function. The energy density is likely to be a smooth function. We'll assume that. A smooth function, the energy density before and after, epsilon and epsilon prime, assume that they are smooth functions of each other. In other words, if you know the energy density before you do the adiabatic transformation, the adiabatic change on things, then that should tell you the energy density afterwards. So that means that epsilon is a smooth function, let's just call it f, of epsilon prime, or vice versa. That's all we really need in order to make the argument. Okay, let's talk about the width of the distribution of epsilon prime, of epsilon, not E, but epsilon. They're only related, they're very closely related. They're simply energy and energy density. E is equal to V times epsilon. But let's see if we can estimate the width of this distribution. Let's begin with the width of the distribution. First of all, let's draw a curve. Here's epsilon prime, here's epsilon, and assume it's a smooth function. The energy densities before and after the adiabatic change. Okay, now, energy is V times epsilon. What about the width of the uncertainty, or the width of the distribution, the width of that profile of that function, delta E? How big do we expect the fluctuations in energy to be? Anybody got an idea? Well, there is a heat capacity formula. Yeah, don't go back to the heat capacity formula. It's not, it will get you there. It will get you there. But just doing statistics, what would you expect? You have energy is a large number. Energy is proportional to the number of particles, okay? Right, you expect that the fluctuations be of order the square root. All right? Square root of volume. Volume being proportional to the number of particles at fixed density. All right, so we take the square root, but the fluctuation in energy should be of order the square root of the volume. Times something, doesn't matter what, but order the square root of the volume of the system. And now let's think about the fluctuations in the energy density. To get to the fluctuations or the uncertainty in the energy density, we divide energy by volume. So we just divide by volume. The uncertainty in energy divided by the volume is equal to 1 over the square root of V. So this means that we're only interested in a range of energy densities which are of order 1 over the square root of the volume. As the volume gets bigger and bigger, and the energy densities energy density is an intensive quantity. It doesn't vary as you make a system bigger and bigger at fixed temperature, for example. So as you make the system bigger and bigger at fixed temperature, make the system large, many, many degrees of freedom, then the range of energy densities that are important under this curve becomes narrower and narrower and gets squeezed down by amount 1 over square root of V. Under those circumstances, as long as the energy after adiabatic transformation is a smooth function of the original energy density, then you can approximate it by being linear. Because there's such a narrow range of energy densities that you can always approximate it when the system becomes large enough by a linear function. Once you've approximated it over the relevant range by a linear function, then this argument here works. Okay? So the key to it is that we must be dealing with large systems. Now, what about small systems? What about small systems? If the small system is part of the large system, all right, first of all, if you take a small system, a handful of degrees of freedom, you isolate it or insulate it, and then make an adiabatic change of some sort, it will not stay in thermal equilibrium. All right, the probability distribution for the small subsystem will not be in thermal equilibrium, period.
Let me ask a very naive question. So what? What's the significance of staying in thermal equilibrium?
Well, that's an assumption in thermodynamics, that if you vary a system slowly, it stays in thermal equilibrium. We've used that over and over with the idea that that varying the parameters of a system leaves it in thermal equilibrium. Otherwise, we couldn't use thermodynamics to study it after we have made a adiabatic change in the system. For example, we defined pressure to be the derivative of the energy with respect to volume in an adiabatic change on the system. Adiabatic change on the system means now you just vary parameters, but we also assumed that the system stayed in thermal equilibrium so that we could relate it to the derivative of the free energy with respect to the volume at fixed temperature. In that derivation, it was definitely assumed that the system stays in thermal equilibrium and that all that happens to it, it stays in thermal equilibrium, and the entropy stays the same. Well, we know the entropy stays the same, but we don't know that it stays in thermal equilibrium until we make an argument. So it's all of thermodynamics would go down the tube if systems didn't stay in equilibrium when you make gradual changes, for example, in the volume.
So our classical thermodynamics, those tools kind of, we push them aside. But then there must be these interesting cases where it doesn't stay in thermal equilibrium in these small systems.
Well,
I can't visualize what that means.
It means that the probability distribution afterwards, when you make the change, so here's the Gedanken experiment. Let's imagine an experiment. This is not something we're going to go around doing easily in the laboratory, but you can. Yeah, you can. Yeah, okay, let's take an example. You have a single atom, and the single atom has many energy levels. All right? It's in equilibrium with its environment. It's being kicked around and whatever it's doing. And if you ask what the probability that that atom has a particular level, what's the probability for different energy levels, it will be the Boltzmann distribution. It will be the Boltzmann distribution because a small atom is an example of a small subsystem in thermal equilibrium with its environment. So its probability distribution for the different energy levels will be e to the minus beta e sub I. If you measure the energy now, that's exactly what you are. Of course, you might imagine many, many atoms. You can't do an experiment on one atom. You do an experiment on many atoms, and you see how many of them have each energy. And it will conform to this. Okay, but now you take the atom and you take it out of contact with its environment. It's not so hard to imagine how you might do that. You simply move the atom out of the container of material that it's in, interacting with other things. You isolate it. You don't look at its energy level. So far, you don't know what its energy is, but you take it out of contact with its environment, and then you look at its energy. Well, it'll be exactly the same. You haven't done anything to its energy, its internal energy. It'll still be e to the minus beta e, because you haven't done anything to it. Okay, but now we're going to do something to it. Don't look at the atom yet, but put it in a magnetic field. It's an isolated atom. It's not in thermal contact with anything. It's insulated for all practical purposes because there's only vacuum around it. And now you put it in a magnetic field and you vary the magnetic field. The effect of varying, or electric field, the effect of varying the electric field is to vary the energy levels. It's an example of an adiabatic change. You slowly ramp up the magnetic field and each atom's energy level change. All the energy levels change. Then, after you've ramped it up like this, being very careful not to allow it to interact with its environment, you then measure the energy of each one of these atoms, and you'll find out that the probability distribution is exactly what it started with, but in terms of the original energy, not the final energy. So the implication is that that atom will not be in thermal equilibrium. It will not have a temperature. It will be out of thermal equilibrium, and it will have a different entropy than you would have expected had it stayed in thermal equilibrium. You can track what its energy, what its average energy is, but its average energy and its entropy, the relation between the average energy and entropy will not be that of thermal equilibrium. So that's a Gedanken experiment. The question here is not what happens when that occurs. That you can follow. The question is, why do any systems remain in thermal equilibrium? Why do any systems remain in thermal equilibrium? Now, the example of the atoms was a little, well, it wasn't artificial. It was a good example. But I've imagined the atoms didn't interact with each other. After I took them out, the whole bunch of them, I imagined they didn't interact with each other. So they didn't provide their own heat bath. All right? Let's suppose we took a system, we isolated it in the same way, ramped up some magnetic field or whatever, but allowing the subsystems to interact with each other. Then what happens? Then they largely stay in thermal equilibrium. It becomes a single big system. For a single big system, even though the energies may not be linear, as long as there's a good notion of energy density, and the energy density is a smooth function before and after, then the fluctuations in energy density are small enough that you can pretend that this relationship is linear. That is the bottom line. Systems stay in thermal equilibrium if they have lots and lots of degrees of freedom, so that the energy fluctuations are very small by comparison with the energy itself. In other words, they stay in equilibrium if this peak is narrow enough. If the peak is narrow enough, then over the range of the peak here, you can assume that the final output energy and the input energy are linearly related. Okay, that's just the rather dull answer to the story. Yeah.
I was looking at Feynman's book on, and in the chapter on thermodynamics, he discusses Carnot cycles and things of that sort. And he used he talked about the adiabatic phase of the Carnot cycle and used the term temperature. He said the temperature falls as you pull the piston out of the thing. So this would have to be a case of this sort here in order to work.
Sure. Yeah.
I mean, clearly it does work, I mean, because the whole theory is
Right, but it's dependent on the gas having a lot of molecules. And people speak about the thermodynamic limit. The definition of the thermodynamic limit is that the system is big enough so that the fluctuations in the various quantities are small by their own, by comparison with their values. Right? So it's only in that limit that the system stays in thermal equilibrium. It's a dull answer. It's not terribly interesting.
I don't know if you want another example of something that could get out of equilibrium, but if you had a gas in some kind of a chamber with that's trapped on one side, and then somehow or another opened the gate so that the gas was no longer confined to half the chamber, then you clearly wouldn't be an equal, because you wouldn't have the pressures on the end walls of the container.
That's a different system. That's a different situation. That's a situation when you make a sudden change.
Right.
Right. So making a sudden change certainly kicks systems out of equilibrium.
Right.
But they will return to equilibrium, but at a different temperature. Now we're talking about making a very, very gradual change. Okay? A very, very gradual change. At every instant, the system will stay in equilibrium in the approximation that the fluctuations are much, much smaller than the energy itself. In other words, when this distribution is narrow enough, then over the range of interest, any function is linear.
But the question then arises, what's sudden, what's gradual?
Right.
Sudden means it's large compared to the time, basically the speed of the process.
Speed of sound.
If you're talking about a gas, we're talking about the piston has to move slow relative to the speed of the molecule.
Well, it's the speed of sound. Yeah, speed of molecules and the speed of sound is about the same. That's right. Yeah. For example, sure. If you move the piston with a velocity faster than the speed of sound or faster than the speed of molecules, then, for example, you could, here's the piston, here's the molecules. You suddenly jerk the piston out, and you certainly create something out of equilibrium. The molecules don't follow it because they don't move that fast, and you just create a region which is empty, and all the molecules are in here. That's not equilibrium. Far from it. But if you wait a while,
Even if it's isolated, if you wait a while.
even if it's isolated, what will happen if it's isolated?
Now you get parts which are in equilibrium with the whatever energy happens to
That's
be
right.
in the
That's right.
thing at the time.
That's right.
Then becomes the energy which is the driving energy and which defines
The equilibrium.
the equilibrium.
Yeah. So the temperature will change to adjust to the new volume with the energy. In this particular example, where you pull a piston out suddenly, you do no work on the molecules, and so it's the energy which doesn't change, the kinetic energy in that particular example. All right? But it's kicked way out of equilibrium. It's got a larger volume, same energy. It's not supposed to have the same, an equilibrium. It would have a different temperature. But the kinetic energy of the molecules is whatever it was, but it will readjust. So,
If you're just had a pure gas, pure ideal gas, then it's not even an approximation. It's exactly EI is equal to B times EI prime.
right. Of course, an ideal gas, a real idealized ideal gas, would not come to thermal equilibrium. It's always assumed, well, what will happen? No, a real ideal gas will not come to thermal. You need interactions between the particles to redistribute the energy among them. So when one says that a system like an ideal gas comes to equilibrium, there's always an assumption that the parts of the system interact with each other. If they don't interact with each other, then it takes an infinite amount of time for it to equilibrate.
Yeah.
In fact, you'd have what you have is the equivalent of a pendulum, because the molecules would slosh back and forth
Right.
forever.
Right. They just slosh back and forth forever. Right. So you need interaction between the molecules, but you don't need much. You don't need a lot of interaction between them. Just as long as they have small cross sections, it'll slosh a few times, and then it will equilibrate.
The energy level for an ideal gas, we had a paper here, and it looks like it's inverse L squared. L, I guess, is the length. I guess he has it in a well of length L, and it's essentially.
That's the ground state. Well, any given energy level is inverse L. Yeah.
Over L squared.
That's
You
one
look at
particle.
That's for, let's see, the energy eigenvalue.
That's the energy level of a single particle.
Okay. Oh, I see. And you're going to be talking about the energy level of the entire gas.
Yeah.
So that would not necessarily. Okay.
It's the large systems of many, many degrees of freedom in which first of all, in which
A single particle would be in equilibrium.
would or would not?
Would.
Would under what circumstances?
It would satisfy that equation right there with A equals 0 and B equals to, I guess, the ratio of L squares, before and after. if L is your control parameter.
As a matter of fact, it would, but that's a rather special case. That's right. If the particles have any interactions between the potential energies will not be governed by that same. So that's kind of special to free particles, right?
You said also the photon gas would be that.
Yeah, the photon gas, and so some simple systems, it's just true in a trivial kind of way. But for any kind of interacting systems, the potential energies won't do that.
And just a general comment. In this example here, you said if there's a large number of particles, and if it's very adiabatic, and if this and if that, it seems that with this example and a lot of other examples, there's so many constraints placed upon the system in order to make the classical statistical mechanics.
No. There's almost no constraints in order that statistical mechanics works as long as you use it right. If you're trying to argue about an adiabatic change in a system, then there are a lot of constraints. But what do you mean by adiabatic? Adiabatic means a very, very special thing. And look, the first constraint is always that the systems we're talking about have large numbers of degrees of freedom. Now, that doesn't mean we can't isolate and look at a small subsystem. We can look at a single molecule if we like, but the things which come to thermal equilibrium and which we apply the ideas of thermal equilibrium to are large systems. Large systems embedded in even larger systems, usually large systems which are embedded in even larger systems to keep them in equilibrium. But sometimes we might just want to look at a single isolated system as parameters change. Yeah, there are constraints, but those constraints have to do with what we're talking about. If we're going to talk about adiabatic, we have to talk about adiabatic.
You're talking about systems that have large systems, they're adiabatic, they have, and it's correct, but there seems to be a tautological kind of thing here where you're defining a certain kind which has a lot of value and not.
No, is it tautological? No, it's not really tautological. For example, when one says that the pressure is the derivative of the energy with respect to a volume in an adiabatic process, and that's the main way we used it. That's the only way we used adiabatic processes in this course. We talked about things like pressure being the response to a change in volume at fixed entropy. Right? Why is the pressure the derivative of the energy with respect to the volume at fixed value of the entropy? It's because fixed value of the entropy corresponds to an isolated system whose energy levels just are governed by F equals ma, basically, the change in the energy of a system, right? And that there's no contaminating things going on with the environment. So we used the idea that adiabatic systems stay in thermal equilibrium only for that purpose. That's the only place we used it in this class. But you're allowed to ask, why does a system under an adiabatic change stay in thermal equilibrium? Why do you assign it a temperature? Why do you assign it a partition function? Why do you assign it a probability distribution governed by the Boltzmann distribution? And that's the answer.
That makes total sense.
Right.
But for example, like you take a balloon full of gas, it has a certain entropy, and you gradually shrink it down to half the size, it has the same amount of entropy.
Yes.
Okay. Now, I know my examples, I know it's incorrect for a lot of reasons, but if you keep shrinking it down small enough, very slowly, it'll get to a critical mass where it becomes a black hole, which has a different amount of entropy. And there's lots of reasons why it's not true. I'm making an absurd example how this stuff only works in an environment that's sort of something that it's mesoscales that's comfortable for us, and any other scale it doesn't seem to work very well. So my question is there something equivalent to this that works at very small or very large scales?
Well, it works at every scale as long as the conditions for an adiabatic change make sense. Now what happens is you actually squeeze something out. First of all, gravity has all kinds of problems in thermodynamics. Even just Newtonian gravity. Newtonian gravity does not have a good thermal equilibrium. The mutual long-range attractions destroy the thermal equilibrium. They make everything want to collapse. So gravity itself is a disastrous thing when you're thinking about thermal equilibrium. It leads to the concept of negative specific heat. All right, let's come back to negative specific heat in a minute, but yeah.
Well, I was going to suggest that it seems to me that the stars in the galaxy are not behaving as a gas. And what you just said about gravity is how you would explain that?
Well, to some extent, the stars in the galaxy are behaving as a gas. If you look at the probability distribution for the velocity of stars, it is more or less a Boltzmann distribution. But in general,
The barred structure.
yeah, it's not. No, it's not in thermal equilibrium. It's certainly not. It's gravity which keeps it from being in thermal equilibrium. Gravity has an odd. Systems under the influence of gravity have an odd behavior. They have negative specific heat. Negative specific heat is a very, very peculiar thing. A system can't really have negative specific heat, and yet gravitational systems do. Let me tell you why they do have. Supposing you have a object and something orbiting around it. It has some kinetic energy. Okay? Supposing it loses energy, what happens to it? Supposing, for example, it radiates away some energy. What happens to the object orbiting around? Does it move in or does it move out? It moves in, right. And in fact, if it were to radiate away, for example, gravitational radiation or any other kind of radiation and lose energy, it would spiral in and eventually hit the central object. But I'm not interested in it hitting the central object. I'm just pointing out that it moves inward. Now, what happens when it moves inward? Does it increase its kinetic energy or decrease? How many people think increase? How many people think decrease? Okay, it increases. Either answer is a possible answer. It's not obvious which it does. Okay, it loses energy, right? But there are two kinds of energy. There's the negative gravitational potential energy, right? And it certainly gets some increased negative gravitational potential energy when it falls in. So its gravitational potential energy decreases in the sense that it becomes more negative. Okay? So how do you know offhand what happens to the potential energy? All you know is that the total energy decreases. Total energy decreases because it lost some energy. Right? Total energy decreases. There's a change in kinetic and there's a change in potential. If the change in the potential energy, the negative change in the potential energy outweighs the change in the kinetic energy, then the kinetic energy might even increase even though the total energy decreases. Okay? Anybody know the relationship between the change in potential energy and the change in kinetic energy? The negative change in potential energy is twice the change in kinetic energy in absolute value. That's called the virial theorem. So the potential energy changes more than the kinetic energy. So what happens is when you lose a certain amount of energy, you lose twice as much potential energy, but you gain that amount of kinetic energy. So if you lose an amount of energy, delta E, you lose that much energy, then the potential energy changes by minus twice delta E, and the kinetic energy increases by amount plus delta E. So when something spirals inward, when it loses energy in this way, its kinetic energy increases. Now, supposing you had, and it doesn't have to be a circular orbit, incidentally. This is true even if it's an elliptical orbit or any other kind of orbit. Now imagine you have a whole bunch of particles moving in the orbit of this central object. Right? They all do the same thing. They lose energy by whatever means. They lose energy by whatever means, and the same thing happens to them. They start to spiral inward, and guess what? Their kinetic energy increases, the potential energy decreases. Now, this is even true if there is no central object, if they're just moving under their own gravity, that as they lose energy, radiate away the energy, for example, a star radiating away its energy, the kinetic energy of things increases. What does it mean about the temperature? That means the temperature goes up. So for gravitating systems, as they lose energy, their temperature goes up. That means the derivative of the energy with respect to temperature is negative. Right? Derivative of energy with respect to temperature is negative. Now, can a system really have that property? First of all, let me point out that that's any system with negative specific heat or negative heat capacity is unstable. It's unstable and it cannot correspond to a genuine equilibrium situation. Let's imagine any system with negative specific heat. Negative specific heat means if you take a little bit of energy away from it, it heats up. If you add an extra little bit of energy to it, it cools down. That's what negative specific heat means. Now let's suppose we have a system with negative specific heat minus specific heat, minus heat capacity. C is negative. The heat capacity is negative. C equals minus heat capacity. All right? Imagine now that it's in equilibrium with its environment. It's in equilibrium with its environment, and it can exchange energy with its environment like any good thermodynamical system. What happens? Well, there are fluctuations. Every once in a while, it'll give a little extra energy to the environment. Every once in a while, the environment will give it a little extra energy, and the energy will be transferred back and forth. And that's what leads to thermodynamic equilibrium. But now imagine the system with negative specific heat gives a little bit of energy to its environment, accidentally, by fluctuation. What happens to its temperature? It goes up. That means it becomes hotter than its environment. Its energy goes up. It becomes a little bit hotter than its environment. Which way does the heat flow? It always flows from hotter to colder. So when this system gives off a little energy, it becomes hotter and it will give off more energy. And it's a runaway. It's a kind of runaway situation. When it fluctuates by giving off a little bit of energy, the conditions are set up for it to give up even more energy, and it's unstable. What happens if it takes a little bit of extra energy? It cools down. Cools down meaning in the sense that its temperature goes down. Now which way does the heat flow? Into it. And again, it's an unstable situation. If it fluctuates, the fluctuation will tend to build up. On the other hand, exactly the opposite happens for a system with positive specific heat. If it absorbs a little bit of energy, it gets hotter, and then energy wants to flow out of it. So that's good. Thermal equilibrium makes sense for systems with positive specific heat. It doesn't make sense for systems with negative specific heat. They can't be in equilibrium with their environment. So all of thermodynamics breaks down eventually for systems with gravity. They're not good thermodynamic systems, yeah. In particular, a system forming a black hole, when it collapses into a black hole, it's way out of equilibrium. And
How do you ascribe a temperature to something like the surface of the sun?
well, okay, yeah. I mean, there are different time scales. It's a question of time scales. The time scale for this instability is fairly long. It's rather long. Now, really, first of all, the sun is certainly not in equilibrium with its environment. Its environment is at 3 degrees. Okay? A star out in outer space, far from anything else. The environment is at 3 degrees. It's not in equilibrium with its environment, and it's radiating into its environment. So if you wait a while, the star will burn out. It's not in thermal equilibrium. It's not being kept in equilibrium by anything.
We still talk about temperature.
Yeah, we talk about temperature because there are different time scales. The time scale for the star to run out of fuel, for its temperature for this instability, the time constant for this instability is rather long. On the other hand, there are processes taking place inside the star whose time scales are very rapid. For those processes, you can simply think of gravity as creating a box, a spherical box in the case of a star, gravity holding things in, and those things are undergoing the usual microscopic processes. Ignore gravity and just think of the system as a box. Take gravity into account in some small ways, but it's just a box of gas being held together by its own gravity. So there are different time scales. The microscopic time scales for particles to interact with each other, which are very rapid, allow you to define a thermal equilibrium in the star which lasts a period of time which is, billions of years. The time scale for a star to run out of fuel is a long, long time.
And the surface of the star is in equilibrium with some region nearby.
It's pretty much in equilibrium with itself, but the star is not really in equilibrium. The temperature is not uniform. Remember, thermal equilibrium means the temperature is uniform throughout it. If the temperature is not uniform, what happens?
That's why
Heat flows.
That's why I said the surface.
Yeah.
Because they're talking about that
Yeah.
part of it.
Yeah, so I mean, that's right. The surface of the star
Well, so it's in,
is pretty much in thermal equilibrium with itself, so to speak. All right? But the fact that it's not in thermal equilibrium, the fact that the temperature varies from one place to another, that tells you that heat flows out. Right. So strictly speaking, a system is not in thermal equilibrium unless the temperature gradients are zero.
Can't you use black body radiation as a black
Sure.
body vector?
Sure, I mean, this is not an obstruction to using thermodynamics for the interior of a star, far from it. But, strictly speaking, technically, and, all sorts of situations you can imagine where this becomes an important thing, namely the collapse of a star into a black hole. That's very far from an equilibrium process.
But the event horizon is in equilibrium.
After the black hole forms.
So it goes from this chaotic thing in
Right, when it goes whoosh, it's way out of equilibrium.
and then it's in equilibrium at that point.
And then it's in equilibrium again, but during the course of its collapse, it's very far out of equilibrium, and the consequence is that the entropy changes a lot. It's very, very far from an adiabatic process. It just collapses. It's much, much more like the situation where you take a plunger and suddenly pull the plunger out. It's very far from an adiabatic process, the actual collapse. But then, after it's collapsed, again, there's this long, long time constant for it to be unstable. And so it can be approximated as being in thermal equilibrium with itself.
All black holes with the same mass have the same entropy?
Well, no.
Sorry,
No.
not spinning or...
If they're not spinning, yes.
Yeah.
Or not charged.
Yeah.
Right. Right. Okay, I wasn't going to get into that, but we've covered some territory. Any other questions?
Yeah, one follow-up question. You did describe, you said, a black hole that somehow mimics the characteristics of the matter infalling to it, that's somehow encoded on the event horizon. You didn't say how.
Somehow.
So if it is encoded, wouldn't mean that the event horizon must have some non-uniformity to it, and that if it has some non-uniformity to it, two different black holes might have different entropy because...
Well, okay.
Does that make sense?
Yeah, it does, but let me answer it by analogy. People say black holes have no hair.
Like my head.
Right. Except a lot smoother than your head. Right. Now, black holes have no hair, and the meaning of that is that black holes, the surface of a black hole is exceedingly smooth with no irregularities. If there are no irregularities, then how do you tell one black hole from another? You can't, as long as its mass is the same. And if there are no distinctions, then there's no entropy, because entropy is describing hidden distinctions. That's what entropy is. It's the hidden information contained in a system. All right, so you could say exactly the same thing about bathtubs full of hot water. Bathtubs full of hot water have no hair. Actually, my wife tells me my bathtub is always full. Actually, used to be. We won't get into this. Let's get off this.
Flow of molecules, right?
Yeah. All right, bathtubs full of hot water have no hair. And the meaning of that is a bathtub in equilibrium. That means enough time has gone that the temperature is uniform, the surface of the bathtub, the surface of the water is completely flat. You look at that bathtub full of water, it has no hair. There's no ripples on it. It's in absolute equilibrium, completely quiescent, completely flat. And from the macroscopic external point of view, it has no hair. It has no structure at all, zero. It's completely described by a small number of parameters. How many parameters? Well, the shape of the bathtub, of course, and all those things, imagine they're given, the volume of water, and the temperature. That's it, or the energy. Energy, let's say energy. The energy in the water, the thermal energy in the water, and the volume of water, and that's about it. Right? So in that sense, bathtubs full of hot water have no hair. But we know what the hair is, the hair that distinguishes between two different microscopic configurations. The information which is there but hidden is the individual molecular degrees of freedom. Okay? What the entropy of a black hole is telling you is that there are microscopic degrees of freedom which are too numerous, too small to see, and that in the coarse-grained sense, in the same sense that the bathtub has no hair, the black hole has no hair, but in the same sense that the bathtub has a microscopic, huge number of degrees of freedom that account for its huge entropy, the black hole must have such a collection of microscopic degrees of freedom. The only question is, what are they? We know how many there are, just the entropy of the black hole. We don't necessarily know precisely what they are.
But if you take two bathtubs with the same characteristics.
Yes.
The
Two
gross
bathtubs with the
entropy
same
will be-
characteristics, okay.
Yeah, the gross entropy will be the same, but if you dig down deep enough.
The
you find some
microscopic, yeah,
fluctuations.
right.
So it's like you're taking big averages, and if you average everything out, you can generalize almost anything you want. So if I want to look at it with blurred vision, I can say, there's no. But if you look at it in more detail,
You can ask a rather precise question. Given the energy and the volume of water in that bathtub, how many precise quantum states are there of the many molecule system which conform to your prescription, namely the energy between some tolerances, whatever that energy happens to be, and the volume given what it is? How many quantum states are there? No, of course there's zillions, but that's exactly what the entropy is measuring. Number of quantum states subject to some criteria. The criteria in the case of bathtub is volume and energy. In the case of black holes, it's just the mass and the angular, and the angular momentum and the charge. But if we forget angular momentum and charge, it's just the mass, that's all. So all black holes are the same from this coarse-grained, squinty-eyed viewpoint where you don't look carefully. They're all the same, but they're distinguished by different microscopic content.
so if you look deeply, they're all different.
They're all different.
Question? In your black hole class, you said that when a black hole evaporates, when it loses half of its mass, if you take account of all the photons, then you can start reconstructing the information in there. Is that correct?
Well, that's a subtle information theoretic issue, yeah.
Okay, so at that point, you could determine one from another, or if you accumulated all that data, then you could determine one from another. Is that correct?
Well, in order to do so, you would have to know far more than is humanly possible to know. You'd have to know the precise, exact dynamics of the system. You'd have to be able to track it and follow it. and do all sorts of things which in practice you really can't do. But in principle, with infinite computing ability and infinite knowledge of the laws, you could do. Same thing is true of a bathtub full of water. Exactly the same thing.
But that would be a difference between black holes, if you, theoretically.
That would be a difference between black holes and what?
One from another.
Oh, one from another, yeah. Yeah.
So then you could say, well, this one is different from that one.
Yeah. But the kind of experiments you would have to do are so out of the ballpark that, right.
It just seems odd that, to say that if you squint enough, everything looks the same. That seems to be not quite right somehow.
I didn't say that, you said it.
I know.
I said if you fix the energy and you fix the volume, count the number of quantum states. Now you may interpret that if you like, if you squint so squinty that you can't see anything except the energy and the volume, then it's the same.
But if I want to look deeply into it, each bathtub will be different.
No?
And doesn't that mean if you don't want to take averages and smooth things out, if you want to look at the actual state of it, they're all different. Now the entropy means that the differences are, on a macro scale, are somewhat small. But if you flip a coin,
There's a man who has clearly never taken a bath.
I take showers, which has discrete blobs of water coming down.
Or quantized.
It's quantized.
You mean that you can see the molecules if you don't squint?
No, I can't
No.
see the molecule.
No.
But that's because I'm taking a shower. I'm not studying the actualities of the shower.
Let's move on before we get into big
Gets them all
trouble.
wet, huh?
Please.
Yeah.
Are you going to talk about negative temperature, perhaps?
Yeah, we can talk about negative temperature a little bit. All right, we have a few minutes to talk about negative temperature. We've talked about negative specific heat. An entirely different subject is negative temperature.
Let me point out two other things that you had mentioned that we might talk about tonight. Bose-Einstein condensation.
I think that's...
Okay, and the connection between particle physics and statistical mechanics?
Yeah, well, I think we've run out of time. But what was I just asked about now? That's a self-contained thing. We didn't talk about this? All right, let's talk about negative temperature. Let's talk about negative temperature. Okay, let's start with a conventional system and ask why the temperature cannot be negative. The temperature ordinarily cannot be negative because the partition function, what is the temperature? One definition of the temperature is that it's the inverse of the beta, which goes into the probability distribution, e to the minus beta e. And then what do we do with that? We sum it over all of the states of the system to calculate the partition function. The partition function is the starting point of all thermodynamics or all statistical mechanics, and it's assumed that it exists. Why does it exist? Why does this converge? It converges because in a usual situation, the number of energy levels does not grow so fast with energy that it overwhelms this e to the minus beta e. In fact, we said that the number of energy levels per unit energy increases and the Boltzmann factor decreases, but at high energy, the Boltzmann factor usually wins, meaning to say at very, very large energy, the integrand, or the summand here, is nice and convergent. There aren't so many states of increasing energy that the sum fails to converge.
That's the thing that failed in the black body situation with the classical black body.
It is what failed in the classical black body. Yeah. The number of states just grew too fast with energy. Yeah, that's correct. So when doing the sum, we always assume that it converges. If it converges, if the number of states increases with energy, yeah, okay, how can we get into trouble? Supposing we made this beta negative, what would happen then? Then we'd be summing sum on I, e to the plus absolute value of beta times e. That would mean that the Boltzmann factor would grow. The Boltzmann factor would grow. If the Boltzmann factor grows and the density of states, the number of states, increases rapidly with energy, then we have no hope that this thing will converge. So the idea of making the temperature negative will just lead to something that's, doesn't make any sense. It doesn't make any sense, can't be in thermal equilibrium for the simple reason that the probability, another way to say it, is the probability distribution is completely unnormalized. It can't be normalized. The sums of the probabilities can't add up to 1. There's no way they can add up to 1 if the probability function is increasing exponentially at high energies. Okay, is there a way around this? Is there any kind of...
Energy cutoff?
Yeah. If, for some reason or another, the energies of the system are bounded from above, imagine they're literally bounded from above, that the energy cannot be bigger than a certain amount, then this sum will not diverge. It will just be whatever it is. And in that case, formally, in the sense of just mathematically, this partition function will exist and make sense as long as for some reason there's an upper bound to the energy. Okay, so what kind of systems have an upper bound to their energy? No real system in nature, incidentally. Some approximate systems, and definitely many, many mathematical systems have an upper bound to their energy. So let me point one out. We talked about magnetic systems. The simple example of a magnetic system was an Ising magnet or even simpler kinds of magnets, which involve simple degrees of freedom sigma, which can be plus or minus 1. And the energy is simply a function of these sigmas. For example, the Ising model, the energy is some number with a minus sign typically, times the product of the sigmas at neighboring points, whatever, some sort of structure like this. Each one of these individual spins is bounded from above and below, cannot be bigger than 1, cannot be smaller than minus 1. And so the energy in each pair is bounded. And in fact, since assuming there's a finite number of pairs, imagine a finite number of pairs, the energy is bounded from above. In that case, the temperature can be negative. Now, temperature being negative has another implication. Let's take a very simple example. I'm going to take the very, very simplest example, that the energy is simply a sum of sigma itself. Not sigma times its neighboring value of sigma, but each sigma has an energy. Okay? That's the energy. If a spin is up, it has one energy. If a spin is down, it has another energy. If a spin is down, it has a negative energy. That's lower. If a spin is up, it has a positive energy. The spin is higher. Okay? Let's think about the entropy. There's a probability distribution. The probability distribution, let's see, what is the probability distribution for ups and downs? Whatever the probability are, let's imagine now a large number of spins. We take out one spin, just study one of them for simplicity, and let's look at its probability distribution to be either up or down, okay? As a function of, what do we want to do? As a function of, the total energy of the system. What do I want to do? Okay, well, let's just look at the partition function. Let's examine the partition function. The partition function is the sum. There are two states for each system, e to the minus beta. Let's suppose if the spin is down, let's say the energy is -1. If the spin is up, let's say it's +1. Then we're going to get e to the minus beta, I think, plus e to the plus beta. That's the partition function, z. This is equal to hyperbolic cosine of beta, or twice the hyperbolic cosine of beta. Okay. First of all, this is just as good for positive beta as for negative beta. Right? Nothing better about positive beta or negative beta. Makes just as good a sense. In fact, it's symmetric about beta equals plus and beta equals minus. Right? So here's an example where negative temperature makes perfectly good sense. The partition function exists for either positive or negative beta. Yeah, okay, I know how to explain this. If you plot the entropy versus the energy, the entropy versus the energy. The lowest energy state is the state with all spins, let's say, down. That's the lowest energy state, and there's only one such state. So at the very, very lowest energy, what is the entropy? 0. What about the very highest energy state? All spins up. Again, the entropy is 0. What does the entropy look like in between? Well, whatever it looks like, it has some shape. Okay. Notice that there is a region in here where the derivative of the entropy with respect to the energy is negative. There's a region here where the derivative of the entropy with respect to the energy is positive, and another region where it's negative. Incidentally, we can write that the other way. The derivative of the energy with respect to the entropy is negative here, and it's positive here. dE by ds greater than 0. Now, remember what the definition of the temperature is. dE by ds. All right? So there's a region over here where the temperature is positive, and there's a region over here where the temperature is negative. It's exactly the same as this, as making the temperature negative in here. But there's a region over here where the entropy increases, and there's a region over here where the entropy decreases as a function of energy. And those are the positive and negative temperature branches.
So the temperature would first start off positive, go to plus infinity, and then go to minus infinity.
That's right. That's correct. Okay, that's about what I was about to say. That's right. So right up on the top here, that's where the energy is maximum. Sorry, that's where the entropy is maximum. The entropy is maximum at the top here. And dE by ds is infinite up here. dE by ds is infinite. ds by dE is 0, so dE by ds is infinite. And right up on the top, the temperature is infinite up here. All right, another way to say it is, suppose you go to infinite temperature. You usually assume that if you go to infinite temperature, that the system has the maximum possible energy, right? But why isn't that true here? All right, the reason it's not true is because really what infinite temperature means is it's maximum disorder. Just maximum disorder, just statistical complete randomness. What happens to this magnet when you have complete statistical randomness? Half the magnets are up and half the magnets are down. That's not the state of maximum energy. The state of maximum energy is when they're all up. The state of minimum energy is when they're all down. And the state of infinite temperature, where everything is completely disordered, is a state which basically has half up and half down. So the infinite temperature is sort of midway between minimum energy and maximum energy. To get from here to here, you have to go through temperature equals infinity. You don't get to negative temperature by cooling a system. You get to negative temperature by heating it up past temperature infinity. Okay? Now what it means for this kind of magnet system is simply that more than half the spins are up. All right? You're beyond the point of complete randomness where half are up and half are down. More than half the spins are up. Okay? It's called population inversion, where the higher energy states of the system, or if you have an example, a real example from the real world is the population inversion of atoms in a laser. You have a laser, you have atoms in the laser, and each atom has two levels, an up level and a down level, a more energetic level and a less energetic level. If you start the system cold, all the atoms will be down. Or in other words, all the atoms will be in the lower energy state, in the ground state. You start heating it, a handful of molecules, a handful of atoms get excited. You keep heating it, you keep raising the temperature and raising the temperature. Of course, we're making an approximation now. The approximation is only that only those two levels are important, which is a fiction. But in the approximation that only those two levels are important, you get to infinite temperature at the point where there's equal population of excited atoms and unexcited atoms, same as this two-level system here. Once you arrange somehow to get more atoms into the excited state than into the unexcited state, that's when the temperature is negative. Now, as I said, it's an approximation. No real thermodynamic system in true equilibrium with its environment ever has a negative temperature. But in the approximation that you can isolate the atoms and pretend that the atoms don't radiate, and the approximation where they don't interact with anything else, then once you establish a population inversion, you say that it's negative temperature. It's not stable. What does it do? It lasers. It starts radiating and it lasers. So it's not really stable. It's far from stable. But if you could switch off the interaction with the radiation field, if you could somehow prevent it from interacting with the electromagnetic radiation and radiating, and if you could also prevent atoms from bumping into each other and doing all the things that atoms really do, then you could talk about the negative temperature. And that's all that negative temperature means. It means more of the atoms are excited than unexcited.
But a temperature implies equilibrium.
What's that?
A temperature implies that there's equilibrium.
Yeah, and in this case, it's really not an equilibrium.
Right. All down, that's very much not in equilibrium. If all the spins are down, that's an unstable.
No, if all the spins are down means
down, well, negative, whatever.
That's the lower energy
that's
state.
The lower or the upper, but both.
The lower energy state is quite stable. It's just a ground state. Not going to do anything.
It's stable, but this distribution is not in equilibrium. Oh, yeah, I see what you're saying. Yeah.
No, if you expose the system and let it interact with a thermal bath, a conventional thermal bath of positive temperature, then it'll come to equilibrium eventually with that bath. For example, it could be black body radiation. These things will absorb and emit radiation. Every time they absorb a photon, they'll jump up. Every time they emit a photon, they'll jump down. And they'll establish some sort of thermal equilibrium with a radiation bath. The radiation bath certainly is a positive temperature, and you'll always be on this side of the curve. Right? The only way to get on this side of the curve is to somehow artificially pump the system into a state of exceptional excitation.
Except it could tunnel through randomly. You could have an odd situation where, for no particular external reason, all the states are at their upper end. It could happen. It's very unlikely.
Could happen. Could happen accidentally. Yeah. Right. But it'll only stay. If it's an interaction with something else, it'll only stay that way for a very brief time.
So what kind of bothers me about I understand what you're saying is that I guess in the kinetic theory of gases, you always think of temperatures being associated with the kinetic energy of particles.
But that's not a very, very general idea.
That's just not true. Temperature has a much other...
Yeah, it's a much broader, I mean, look, one of the important things that you should have taken away from this class is that temperature really isn't just the kinetic energy of particles. It's got a statistical, mechanical, probabilistic definition in terms of entropy, and entropy is a statistical idea or a probabilistic idea of counting the number of states of a system, counting probabilities. So no, I mean, there's nothing very general about the idea that temperature is the kinetic energy of particles. It happens to be true for a class of conventional, ordinary, non-relativistic gases. It is not true, for example, if the particles are moving fast enough that relativity is important. And it's certainly not true in general for a gas of photons. The temperature is not exactly equal to the kinetic energy. But they have the same units, energy and temperature. So it's not too unusual to expect that the temperature and the energy of a particle will be somehow related. They have the same units, but the exact equality, 3/2 kT or something like that, is not a general idea. The very general fact is that the energy of a system is minus the derivative of the partition function with respect to beta. That's the general fact. In the case of a system of particles, even if they're interacting with potential energies, then this often comes out to just be 3/2 T. But it's a rather special and special thing. And in particular, the kinetic energy of particles cannot be negative. So, all right. Okay. Now, I must say that in this idea of negative temperature, you're making all sorts of assumptions about what you can ignore. The atoms have kinetic energy. They have vibrational energy inside a lattice and so forth. You're assuming that the energy of excitation of the atoms cannot be easily transferred back and forth between the other forms of energy, that the atomic levels, the two-level systems, form a closed system which doesn't interact very readily with the other degrees of freedom. And that may or may not be true in a real situation. If it's true, it won't be true for very long. They tend to be unstable systems. Let's see. Let's see, if you're in this negative energy region here, the negative temperature. No, I was going to say the specific heat is negative, but it's not. It's not. It's not.
But if you have the constraint here that the ground state is the most probable, what that does to that distribution is just shifts it close to the y-axis. It's still...
Well, negative temperature is exactly the situation where the ground state is not the most likely. Right. But as I said, in order to create it, you don't create it by having a system equilibrate with some heat bath. All real heat baths have positive temperature. You create it by pumping some energy in a very non-equilibrium way into the laser by special techniques which are far from equilibrium techniques. And really all it means is that more of the atoms are in the excited state than are in the unexcited state. That's all it really means.
Wouldn't that be a good example of if you had a tool like a generalized temperature that was a function of the entropy as well as the energy that would... In other words, the temperature, it's related to the energy given that it's in thermal equilibrium, which means the entropy is maximized. Okay. In this situation, when you're not at that high point, the system is not in thermal equilibrium.
Well, it's technically in thermal equilibrium when it's over here.
Why would it be that? Because the entropy isn't maximized.
Yeah, the entropy is maximized for a given amount of energy, but now the energy is greater than the energy would be at infinite temperature. Yeah, I mean, it's still governed by the Boltzmann distribution, but a Boltzmann distribution with a negative temperature. So As I said, the only obstruction to writing down mathematically negative temperatures is that as a general rule, if you put a negative temperature over here, the partition function would just be infinite, just because the series wouldn't converge. If, for some reason, there's an upper bound on the energy, then negative temperature makes mathematical sense, but it still may not make the same physical sense that it would for positive temperatures.
It wouldn't be very cold.
It wouldn't be very cold. It's hotter than infinite. Right.
You know, consider a following situation where you have a laser gain, a helium band laser, and maybe you're exciting it optically, and so you've got a constant bath of photons coming in and exciting the states in the gas.
Right.
A little bit of energy going up the solid. If you were to take that gas and divide it into smaller volumes, wouldn't all those volumes have the same statistics? And in that sense, wouldn't that mean that it's an equilibrium?
Equilibrium with itself, but not equilibrium with the environment of the laser.
Because we're putting energy in? Is that the...
Well, yeah, I mean, my only point is that you couldn't get this system to be at negative temperature by placing it in a bathtub of water at negative temperature. You wouldn't. The way that you get systems at negative temperature is not to let them equilibrate with systems in thermal equilibrium, but is to do something very far from thermal equilibrium. And then, yes, if you manage to get the system into this population inversion configuration, I presume that the molecules will exchange some energy and do some things which will get it into, which will get the pieces of it into thermal equilibrium at the negative temperature. But they won't be in thermal equilibrium with an external heat bath. That's all I meant, yeah. They may define, the extent to which they define in any sense, in any useful sense, a heat bath at negative temperature, that's a peculiar question. I mean, I'm not sure if you took some, maybe. We'd have to invent a case and see what it would mean. Can we bring another laser to thermal equilibrium at negative temperature by putting it in contact with a laser at negative? Maybe, I'm not sure. Interesting question. Or better yet, can we just put a single atom into thermal equilibrium with the laser in such a way that that atom would have a larger probability of being in its excited state than its ground state? I think yes. I think yes, that you can think of the laser as a heat bath at negative temperature. But that
Could you pass the infinite temperature by exposing a set of molecules in positive temperature to a larger degree of negative temperature heat bath?
Wait, say it again?
Well, by equilibrium, if you had a heat bath that was way on the far end of the negative temperature scale and bring in a few atoms into that heat bath, would you be able to bypass the limit of the infinite temperature?
Yeah, I think so. I think so. Yeah, I think you could take those extra few atoms and think of them as being in a heat bath in the negative temperature environment. I think that's right. Right. No, my only point was that you can't, that there's no way to make the laser laze by putting it into some substance, some ordinary substance at negative temperature. Won't work. Okay. Have a good summer.
For more, please visit us at stanford.edu.